Hello, everyone. This is the lecture for section 5.4, integration formulas and the net change theorem. Okay, so like I said from the previous section, right, just how we did with derivatives, right? For the very first couple sections of derivatives, we were doing them all by hand. So we had to do the limit as h approaches 0, f of x plus h minus f of x, all divided by h, okay? After, I think it was section 3.3, we started just using the shortcuts on and on and on. Same thing for this. So after last section, after section 5.3, okay, we are no longer doing the integral by the little squares. We're doing them by shortcuts, okay? So first thing I want to do is review some of those shortcut integration formulas that we covered in section 4.10. Okay, here's a couple of them. These are just like the very, 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 very basic ones, right? These are all at the end of section 4.10. I added, I think, one or two from that list here. Okay, so just make sure you know how to use these, how they work. Okay. Let me scroll this down a little bit. So what I would want to say is this, that, I mean, this is a very few of them. It's not very exhaustive at all, okay? A much more exhaustive reference packet where it has many, many, many more integrals, just in case you ever need them, right? Can usually be found inside either the front end or the back end of a calculus textbook, okay? I've chosen one out for you guys to have, okay? I think it's like a good 10, 12 pages of just math facts. I believe it's got a good 10 pages worth of just calculus. Okay, so what I've done is I've grabbed that that packet. I've called it the calculus reference sheet, and I've put it in the Canvas files in our Canvas page. Okay, so if you want, right, if once you guys get into Calc 2, you're going to want to maybe print this out, try to print it out double-sided, or just have it somewhere on your desktop just for quick access, okay? That packet is much more exhaustive than these 8 that are right here, okay? These are the most common ones. So if you need any more, head over to the packet, okay? The first thing I want you guys to do is just practice the integral. Practice the integral. That's it. Okay, so look at the formulas from above. Let me put those in frame too. These formulas from above, right? And then practice doing these integrals just flat out. Okay. Remember that these are indefinite integrals, so you have to do the plus c at the end. Make sure you don't forget the plus c. Okay. So what I want to cover in this chapter, in this section really quick, is what's called the net change theorem. Okay. What I do want to recall is the fundamental theorem of calculus part 2. It's the evaluation theorem, right? That states that if big F of x is an antiderivative of f of x, so then if you take the derivative of big F, you get little f, right? Then the evaluation theorem states that we can do this. The integral from some point A to some point B of little f of x, right, is equal to big F of B minus big F of A. Okay. What we get to do now, what the evaluation theorem, or sorry, what the net change theorem says, right, is we get to look at little f of x, right, as big F prime. Okay. That's the only thing that changes, really. So if you notice, these two statements right here are exactly the same, with the exception of this difference right here. Okay, so let me read this out. And let me summarize really quick, right? The net change theorem states that the new value of a changing quantity equals the initial plus the integral of the rate of change. Okay, so the new value of a changing quantity is going to be its initial value, right, plus the integral of the rate of change. Okay, so if I do it with the equation that's on the left, it makes a little bit more sense, right? And if I do it with the equation on the right, right, you guys can see that this is sort of a corollary to the original evaluation theorem, the second fundamental theorem of calculus. That's all it is. Okay, now to interpret what the heck this thing says, right? What it says, right, is that we are now looking at little f, right, being the derivative of big F. We're looking at the little f as a rate of change, right? So then therefore, right, if we integrate the rate of change over the interval AB, right, then that outcome, the outcome of this integral right here, the integral of that right there, right? The outcome of it is the amount change of f of x. It tells you how much it has changed. Okay. It tells you how much it has changed, which makes sense, right? Because if, taking, this is what we're going to use right now, right? In the next example, let's say you had a velocity, right? And you integrate the velocity, right? Then the outcome should be a position, right? And in particular, it's supposed to be how much position has changed over from A to B. Make sense? So that's exactly what we're going to get into. We're going to need a couple definitions from physics before we move on. Okay. Come on. There we go. I don't want to scroll down too much. There we go. We need two definitions from physics. Okay. The first one is the definition of distance, and the other one is the definition of displacement. You're going to hear it in your very first physics class if you haven't taken it yet. Okay. If you have taken it, you've probably been already using it for it. Okay. So distance, right, is the total distance traveled. Okay. And displacement, right, is the difference between the starting point and an end point. So the way that I like to explain it is this, right? So let me take a look at displacement first, right? So the displacement, the definition or an example of displacement would be like, let's say I, right now, jump into a spaceship, head to the moon, and then fly right back and land 5 feet from where I first started. Okay. Then that means my displacement is just 5 feet. Even though I went to the moon and back, right? My displacement, my difference between the start and end point is just 5 feet. Okay. The total distance traveled, though, is the entire distance to the moon and back. You see the difference? Okay. So just keep that in mind, right? When we're doing these next two examples, or this next example here, okay? This is actually a very common application. I know it's really annoying, of the total area versus the net signed area of a function, okay? So let's go ahead and jump into the example here. We have a particle, right, along a line, so that its velocity is given by that equation right there. V of t is equal to that right there. Meters per second on the time interval 0 to 6 seconds, right? So the first thing I'm going to do is I'm going to compute the displacement, right? Now, I want to observe a couple things here, right? So if you guys remember, we need it from 0 to 6, right? So we need from 0. So the graph here, I should put this here. This is V of t, right? We need it from here to 6 right here. Okay. Now, what I want to sort of observe here is this, that this little portion down here is negative. Okay. That right there is negative, right? While this area right here is positive, right? So just a quick interpretation here, right? In this area, this particle, right, is moving in the negative direction. It's moving backwards. You guys see that? And over here, since the velocity is positive, right, it's moving in the positive direction. It's moving forward. So just to point that out, because that's going to be something real important that we're going to need to do in part B, right? So let's do part A first, okay? And let me explain what's going to be happening here. So the first thing we want to do is find the displacement of the particle over 0 to 6 seconds. Okay, so then that means I'm going to do the integral, right, from 0 to 6 of my function v of t dt equal to the integral from 0 to 6 of t squared minus 2t minus 8 dt. Okay, so I'm off to the races, right? The integral of this thing, right? If you remember the equations from before, let me actually write it over here because we're going to need to do the math in a second. Let me clear out my desk a little bit. There we go. It's annoying when you have stuff on your desk and you're trying to write over it and then you trip over like, I don't know, breadcrumb or something. Oh man. Okay. Okay, so the integral of this is going to be t cubed over 3 minus 2 times t squared over 2, right? Minus 8t, all evaluated, right, from 0 to 6. Okay, so that means, let me go ahead and plug in stuff here, right? So it's going to be 6 cubed over 3 minus 2 times 6 squared over 2 minus 8 times 6. That is for 6, right? Minus everything for the 0, right? So then this is going to be 0 cubed over 3 minus 2 times 0 squared over 2 minus 8 times 0. Okay, all of the stuff over here is 0, so that goes away. We know that this is going to be 0, right? Therefore, we have 6 cubed over 3 minus 6 squared minus 8 times 6. Okay, and if we put that in our handy dandy calculator, we get something. 6 cubed divided by 3. So this is going to be 72 minus 36 minus 48. 2 minus 36 minus 48, negative 12, right? Okay, so what did we do here? We found the displacement. So the difference between, right? Oh, meters. Forgot. Okay. So suppose this this particle started somewhere, right? At t equals 0. Let me go ahead and use my space pen. Suppose that the particle started somewhere at t equals 0. And then at t equals 6 seconds later, it's somewhere else, right? What we just found was the difference between those two positions. So it started at t equals 0 somewhere. It ended at t equals 6 somewhere. The difference between those 2 points, the starting and the ending point, is 12 meters in the negative direction. So from the start to the very end, he's still 12 meters, 12 meters back from where he started. Okay. Okay. Now let's go ahead and find the total distance. Okay. Let's go ahead and find the total distance. Now we have to take care of, and this is where we're going to have to see the difference between the total area and the net signed area. Okay. So part A was our net signed area. Okay, that's sort of the example of our net signed area. That because the velocity was negative, right? Because the velocity was negative, he was moving backwards. This particle was moving backwards to begin with, right? So that distance, right, should be negative, right? At t equal 4 seconds, if you guys look at the graph, at t equal 4 seconds, that's where he starts moving forward again. That's when the particle starts moving forward again, but he didn't move forward enough to cancel out the negativeness that he did from 0 to 4 seconds, right? So he's still at a deficit. He's still 12 meters behind where he started. Does that make sense? That's the net signed area. It didn't take into account that between 0 and 4, right, the particle was moving backwards. Okay. Now we do have to take into account if our particle is moving backwards. Okay. So in order to find the total distance now, right, we need to find basically the distance that he traveled in the negative direction, right? We know that we want to take that as a amount of distance, right? So we need to turn it positive, even though we know that it's going to be negative, right? And then from 4 to 6, he was going positive anyway. That number is going to be positive. We're good to go, right? So that's what the total distance is, right? So what we need to do here, right, is this. I'm going to go ahead and actually, let me leave the graph up. There we go. So the first thing I want to do is find the integral from 0 to 4 of v of t dt. Okay, and that integral is going to be the integral from 0 to 4, right, of v of t, which was t squared minus 2t 2t minus 8, yeah, dt. We know what the integral is, right? T cubed over 3 minus t squared minus 8t, all evaluated from 0 to 4, right? And we're off to the races. So 4 cubed over 3 minus 4 cubed plus 8 times, minus 8 times 4. Ooh, almost got lost there, right? That's for the 4, and then minus the 1 for the 0. So 0 cubed over 3 minus 0 squared minus 8 times 0. All of the stuff on that tail end, that's 0, right? So I get left with 64 over 3 minus 64 minus 32. Okay, and this is all equal to, let's put that into our calculator, 64 divided by 3, okay, minus 64 minus 32. Okay, and that's going to be negative 74.66 meters, right? So notice what I just did, right? I got a negative answer because, right, you take a look at the graph, the particle was moving in the negative direction. So from where he started, he moved 74 meters back, okay? That's the amount of distance that was traveled in the negative direction, right? So then now we get to do the positive, right? So that's going to be now the integral from 4 to 6 of v of t dt. Okay, so that is going to be equal to the integral from 4 to 6. Let me now scroll it down since we have all the stuff for it. T squared minus 2t minus 8 dt. We know that this is going to be t cubed over 3 minus t squared minus 8t, all now evaluated from 4 to 6, the positive, the times where he was moving, where the particle was moving in the positive direction, right? And that's going to be equal to So 6 cubed over 3 minus 6 to the third minus 8 times 6. Minus 4 to the third over 3 minus 4 to the third minus 8 times 4. Okay, so what we get here now is this. We have the answer for this for above, right? That is going to be negative 12, the very first one. So it's going to be minus 12, right? Minus the one for 4, so minus 74.66 meters. Okay. And this is equal to, let me do the math here. So this would be 74.66 minus 12, 62. Oh, 62.66 meters. There we go. There we go. Okay. So here's our answer there. Okay. So now, notice what I did, right? Let me go back up to the graph, right? The first thing that I did, let me erase the points here so I can be a little bit more indicative of what I'm doing. We know that from 0 to 4, this particle was moving in the negative direction, right? Because the velocities are all negative here, right? The amount of distance that our particle went between 0 and 4 seconds was negative 74.66 meters, right? So it went backwards that many meters, right? And then from 4 to 6, he started moving in the positive direction. So he did an about face, the particle did an about face and started moving toward the positive areas, right? Okay, and that distance is the 62.66 meters. Okay, that distance is the 62.66 meters. Okay, so now we get to finally answer the original question, the total distance. So the total distance, write that down. The total distance. So, or hopefully you guys recall, I think I said it in the previous section that when we do net signed area versus total area, right? One of them is just a flat out integral without any messing around with it, right? The other one is the one that the total area, right, is the one that we have to sort of compute it out, but then we might get negative areas, so we have to just turn it positive because we know we need to, right? This is one of those instances. I know that my answer, right, for the negative direction gave me something negative, right? But I want the total distance. I want the amount of distance it traveled in the negative direction, right? So I just get to turn that 74.66 into a positive value. So then the total distance is going to be 74.66 meters, right? Plus the 62.66 meters from the second half. So this is, let me sum this up really quick. This is the amount of distance that it traveled in the negative direction, right? And then we're adding it to the amount of distance he traveled in the positive direction. And if we add these two together, let me grab my calculator. 0.66 plus 62.66, 137.32. And we are done. Okay, so notice the difference between the two values, right? Between the two answers. The first one, right? The first one, our particle started somewhere, right? And ended somewhere at t equals 6 seconds, right? The difference between those 2 points is just negative 12 meters. So they were 12 meters apart from start to end. Okay. However, our particle as a whole went backwards 74.66 meters, and then forward another 62.66 meters for a grand total of 137 and a third meters traveled. You guys see the difference? This is a pretty good example of the application of the total area versus the net signed area. The net signed area is the one that took away distance, right? So notice how the distance between these two values right here, the ones that are underlined in orange here, the ones that I'm gonna highlight in pink right now, the difference between those two distances is 12, right? You guys see that? And it's 12 more, right? In the negative direction that it was traveling, the 74.66, right? Hence the reason why they're, from start to finish, it was only 12 meters difference. Okay. Okay, I believe that is it. The next thing that comes up is lecture questions. Yay. Okay, so if you guys have any questions, come visit me in my Zoom room, in my office hours, in my lab hours, or send me an email, something through Canvas or through the discussion sections, okay? Besides that, I'll see you guys around and hope you guys are studying real hard.